A blue dot travels around and finally dots the eye of text, Indeed. At Indeed Eng, Tech talks at Indeed's Austin headquarters, engineering.indeed.com.
Thank you.
Man in a suit jacket speaks from a stage where signage reads, "We help people."
So today I want to talk to you all about from data to deployment, full stack data science.
Presentation slides begin.
And so full stack is a term that's used a lot with software engineers to kind of describe that they work on the entire process. They write code is in the back end to access data, and they write code kind of on the front end to actually show that to their users. So I'm going to try to apply that to data science here today and talk to you a lot about full stack data scientists, who are individuals that work on the entire data science process, and full stack data science organizations that have teams of data scientists and engineers and product managers that work on the same.
Text, Ben Link, data scientist.
So as Donald said, I'm Ben. I've been a data scientist here at Indeed for 3.5 years. I've worked on some amazing problems, and it's been really exciting and great to work with such great engineers and data scientists here.
A bar chart titled Unique Visitors, Millions, has years 2009 through 2015 on the x-axis. Bars increase in an upward slope, with 2009 being at about 20 million and 2015 being at 200 million.
As a reminder, Indeed is the #1 external source of hire. Indeed has grown year over year and is kind of the go-to thing for job seekers to help them find jobs in the US. We service 200 million unique visitors per month. In the US, 80 of them. We have 16 million jobs. We generate 30 terabytes of data a day.
Text, we help people get jobs.
At Indeed, our mission and our focus is that we help people get jobs. Every decision that we make here, whether it's a small decision in a room or a big product decision or a data science decision, we think about this. What would the job seeker need? What's important to the job seeker?
Data science at Indeed.
So I want to begin with talking about some data science examples here at Indeed. I'm walking you through some of the cool stuff that we do.
Indeed site with data scientist in what search field and San Francisco in the where field. Search results 442 new jobs.
So this is kind of a really common page I think that many Indeed users have seen before. It is our search result page. And kind of on this page you can see that we're searching for a data scientist in San Francisco, and we show a number of obvious things. Relevant search results, for example, maybe senior software engineer or data scientist. But there's a bunch of other stuff going on this page that regards to data science. There are things like sponsored slots. So sponsored slots are a way in which an employer can decide to sponsor a single job, and we will show it in a specific slot if it's relevant to their query. But also on this page are things like recommended jobs, where we can show the top jobs for your resume or for your query that you can use to help you find a job faster. And lastly, there's even a salary estimation, which is done using a machine learning model here that shows a range of what we expect a data scientist in San Francisco to be making. So in this case, we show something like $97,000 to $200,000 a year.
Text, applicant quality.
There's a lot of other data science that goes on at Indeed than just the search result page, though. I work on the applicant quality team in San Francisco, and our team is tasked with trying to find out if a job seeker and a job are a good fit for each other. And so we look at things like job data, job descriptions, job titles, information about employers. We take that in combination with resume data, job seeker information, cover letters, and we kind of combine it together with a number of different features to really decide if we think someone's a good fit for that job. And we use this in a number of subtle but very effective ways. One of the ways we use models like this is to emphasize to an employer that a candidate matches their job.
Two names with their locations and titles. The word match beneath one name.
And so on a candidate view page, which is a page that shows the number of candidates that have applied to your job, we emphasize this by showing a green match text. And this is a very subtle change, and it's very surprising, and it was very surprising to us when we tested this, that it has shown pretty significant impact. And so our theory behind this is that when you look at a bunch of candidates and all you see is a name and maybe a position and a location, you don't get enough information to really make a decision about that candidate. And so showing this match text encourages employers to click on this that may have otherwise skipped a candidate. And so we see really nice gains like more clicks and more applies, and more kind of positive engagement and scheduled interviews.
On a cell phone, a job opening for digital graphic designer. Text reads, "Apply from your phone," and "Your resume matches this job."
Another way we use our applicant quality models are to emphasize to a job seeker while they're actually viewing a job on their phone that we think they're a good fit for it based on their resume. So this happens live. You may kind of actually looking for jobs, you have a resume on your phone, and we suggest to you that we think your resume matches this job. And so this allows job seekers to have a good idea if they're a good fit for a job. Maybe they weren't sure if they were. And so we get more clicks from this and we get more interviews from this.
Email reads, "Creditcards.com is looking for a user experience designer, and it looks like your resume may fit the requirements." A large blue "Apply Now" button.
The last example of how we use our applicant quality model is through an email retargeting campaign. And so this is a mobile email that shows that we think this specific role is a good fit for you. We use this in cases in which a job seeker may have looked at a job in the past but not applied to it for whatever reason. So this is encouraging them, hey, we know you looked at this. We think you are a good fit for this, so please apply.
Text, "What does a data scientist do at Indeed?"
So whenever you talk about data science and data scientist, it's sort of ambiguous within industry. What does that person actually do? Are they an analyst? Are they a machine learning engineer? Are they a product manager? And so I kind of want to discuss a bit about what we expect data scientists to do here at Indeed. And remember that our talk is called Full Stack Data Science. So we think data scientists should be full stack data scientists. We expect them to do a lot.
Diagram shows a segmented circle, where the segments are labeled with a data scientist's process.
So I started thinking about the obvious things that a data scientist does here at Indeed, and I started writing them down. And I put it in this nice little kind of cyclical diagram. And I was pretty excited about it. And I realized at some point that it's not really a linear process going between steps. You know, a data scientist may work on generating a hypothesis or exploring data, generating features, building models, deploying models, A/B testing models.
A line on the diagram jumps from hypothesis formulation to analyze labels, skipping gather data and explore data.
But realistically, they don't go in order like that. We want them to, but we kind of have transitions. And so maybe you label some data and you realize that actually I need to go back and think about my problem again. Maybe you do some analysis and you decide that actually is really important. I need to think about how I frame this problem. And so I kept drawing these lines, and I ended up with something like this, which is, as someone eloquently described this, it looks like a dream catcher.
Several lines inside the circle connect different points in the process.
And I kind of think this is how data science works, is that you're working on all these different steps and you're making transitions back and forth. But it's really difficult to talk about the steps that a data scientist does or that a full stack data scientist does when it looks like this. So I'm just going to treat it like it's linear, but keep this in the back of your head that this is actually what transitions look like between work.
An arrow-shaped diagram with 4 steps which begin with hypothesis formulation, then gather data, explore data, and label data.
So any good scientist, and a data scientist is a scientist, first starts thinking about things like hypothesis formulation. What is the business problem? What am I actually trying to solve? And typically they gather data and they explore that data to understand that problem. And even sometimes we add annotations to data. Maybe we decide that we think a job description has a piece of information or not.
Steps on arrow change to analyze labels, generate features, analyze features, and prototype models.
And after we've kind of labeled data, we may do some analysis on that and then really use the understanding of that data to generate features. So maybe we use these features to build a very simple heuristic to solve our problem, or maybe we use it to build a really deep neural network. We can do analysis on those features, understand which ones are most important, and we can start prototyping models.
Arrow changes to label, hold out data, evaluate model, model review, and deploy model.
And any good practitioner of machine learning or data science always has a labeled holdout set that they can use to evaluate the performance of their models. And they do multiple types of evaluation to determine if our model is a good fit for the application we're trying to use it for. So things like quantitative feedback or qualitative feedback. And indeed, we do another thing which we call a model review. And I'm going to talk about this in detail a little bit later. But a model review is essentially asking another data scientist to review your model and give a sign-off to go to production, much like we do for code reviews in engineering. And lastly, you deploy your model, and that's great. So stopping here, I think most data science talks just end here, in that you deployed your model, things are great, we're really excited about it. But realistically, with any piece of software or any model that you deploy, you're not done. You need to think about other things.
Arrow now reads, choose final parameters, /b test model, monitor model, and repeat.
So maybe there's some additional parameters you need to choose for your model. What things should I emphasize? Maybe I want to A/B test my model. And lastly, I want to understand that the inputs going to my model aren't changing over time so that I understand if that's a problem or not. So we monitor our models here in Indeed. And then finally, to reemphasize, this is an iterative process. This is a process that transitions between all of these different states. We expect data scientists to do a lot.
Text, full stack data scientists, 1, prevent handoff mistakes, 2, can contribute on any team, 3, have big picture in mind.
So really kind of reviewing on all of that material, it's full stack data scientists work from the beginning to the end, from getting data to begin with, to deploying a model and monitoring a model when it's in production. So really, what I talked about there was that full stack data science can be done really by an organization or an individual. I want to focus here on why we at Indeed train full stack data scientists that can do this themselves. So an individual that can do all of these different things. There are a couple of important reasons that we've noticed by having full stack data scientists. One of them is that full stack data scientists prevent handoff mistakes. You don't have separate engineering and data teams, and you don't have issues between not communicating effectively. Full stack data scientists can contribute on any team. They can work for a small team or a large team. And lastly, full stack data scientists have the big picture in mind. They can think about the entire problem and the infrastructure necessary to solve it.
1, prevent handoff mistakes.
Preventing handoff mistakes. I want to talk about a motivating example here.
Model diagram with IPython in center of feature extraction and model building. From feature extraction, DB, and raw data.
And so imagine you're a data scientist and you're building a really nice model and you're using IPython notebook and you go ahead and access some data from a database that's available to you. And you do some feature extraction, you build a model, and you're pretty excited about it and you're ready to deploy it. So you hand it off to another team to help you deploy it.
Diagram changes. Web infrastructure in center of completed model and feature extraction.
And in your mind, it looks like this. They just have to add the model to the web infrastructure, do some feature extraction, they access the data in the same way, and everything's great. But what things look like in the real world are a lot more complicated.
Off of feature extraction, data service and JSON data appear.
Maybe there's a service on top of that data. It comes back in a different format. It's JSON instead of raw.
NoSQL now appears atop DB.
Actually, that database that we're accessing for doing analysis and building our models is really a NoSQL store in production. And it's not. This is a replica of it. It's stored in a different format.
New service above data service.
There's a better service, apparently, than the one we thought we were going to be using, so we're actually going to use that one instead, but it returns this data in a slightly different format, has a little different latency profile. So really, we just changed everything. We changed the data in 3 different ways. We changed the format of the data, we changed how we're getting the data, we changed in the raw storage of the data. When we're talking about data science solutions, we're expecting our features to be in the same distributions when we're doing our predictions as we did when we built our models.
On diagram, feature extraction changes to Java feature extraction.
And the last thing is, maybe our web infrastructure is not even in the same programming language as we build our model in. And so with all of these changes, we're really worried. And when we have kind of multiple teams that we're handing off this work between, we struggle with these kind of things. And many data scientists don't ever deploy models. A little later in this discussion, I'll bring up other ways that we've kind of addressed this problem.
Text 2, contribute on any team.
A full stack data scientist can contribute on any team. So for a small team, a full stack data scientist can do things like drive logging of data, help a team decide which things they should be logging from the beginning. They can help drive product decisions. What initial product decisions should we be making? And maybe not even using the data that we have on that team, maybe using external data, maybe using data from another team. And lastly, and the best part about a full stack data scientist is they can get something into production quickly. Your new team can have a machine learning model or a data science solution into production very quickly. But maybe you work on a bigger team, a more complex and mature team that already has some data science solutions. That's great. Full stack data scientists can help you iterate on those solutions, try new models out. And they can recognize the costs of model decisions and feature decisions while they're building them so that when you deploy them, there's no surprises.
3, think big.
Lastly, full stack data scientists think big. They think about the whole problem from the beginning to the end, from accessing data to deploying a model to monitoring a model. And they get to focus on the right problem. They get to focus on a business problem, which involves an actual release of a product.
Practical data science.
I'm going to talk a little bit about practical data science and some of the stuff that we do here in Indeed. But first, I want to start with an example of one of the models that we built, or a class of models that we built. And so one thing is, we build a lot of different classifiers on job description data, and we build a lot of classifiers on resume-based data.
Job description of a senior software engineer.
So here's an example of a job. It's a senior software engineer role. It has a bunch of information about a company. It has a list of kind of what we expect this role, the person in this role to perform, and lastly, what kind of skills we expect this person to have. One of our job description classifiers, and so all of our job description classifiers try to find useful high-level information from these jobs. And so one of our classifiers is trying to predict the min years of experience from a job description. We use this as a pretty easy way to tell really skilled jobs away from new kind of entry-level jobs. So you can see, you can look at things that in this job description, like the 5+ years section, or words like expert or advanced, to be able to predict things like this. So maybe you generate some features that are pretty simple, things like looking for a regular expression of 5+, or looking for a term frequency inverts document frequency. Does the word expert appear in here? Looking at bigrams, so maybe multiple words.
List of process steps with action verbs highlighted in blue.
So we're going to use that job description classifier as a motivating example while we walk through some core kind of ideas around practical data science. We're going to talk about labeling data and the many ways you can do it and how often you should do it. We'll discuss extracting features in one place. So can you extract features both in the deployment and in the model training? We're going to talk about reusing your model building code. So don't write the same IPython notebook over and over again. Take advantage of some software engineering principles, reuse your code. We'll talk about doing soft releases, which is something we do here in Indeed, which allows us to understand models before we fully release them to production. You should always log everything. We'll talk about model validation and the model review I discussed a little bit earlier. And then lastly, how do I monitor my features and my model performance after I've released it? And how often should I retrain my model? So we'll use an example of that min years job description model to kind of go through each of these and show off some of the tools that we use in Indeed to solve these problems.
Label data before, during, and after you build a model.
So labeling. At Indeed, we have this awesome thing, which is that most of our data in our biggest data sets are resumes and job descriptions. These are sets of data in which we can look at them and we can understand them as humans because humans generated them. And that gives us a huge advantage in that we can label this data using other humans or experts who involve themselves with resumes or jobs. And so we label data before we build models, we label data while we're building models, and we label data after we build models. So if you want to understand a problem and you have data that you can comprehend by looking at, one of the easiest things you can do is to label the data yourself. So maybe label things about it, add annotations to it, understand that data, really diving into this data and generating information from it. If you want to build a model and you want to build a supervised machine learning model, the fastest way for you to get labeled data is to label it yourself. And the last part is the easiest way to know that your labels are generated in a consistent way. So I'm not relying on my other users on my website to do things consistently with good faith, is to label it yourself. You know what assumptions you're making. You know what choices you're making to actually put those labels on that data. There are some other awesome benefits about labeling data yourself as a data scientist, and that it encourages feature development. You get to see your data, you get to think about how it's generated, it may surprise you, and you can think about features that may be applicable to the problem you're working on. It also creates a human benchmark. So you know this is how good a human could do at solving this problem. This is how good a human could do and their performance. So now I can try to build a model to mimic that or beat that. The last part about labeling data, especially if you're doing it throughout the process, so not just at the beginning before you build a model, but also at the end so you can evaluate your model, but even after you deploy your model, is that changes in the labels and changes in your data are visible when you're doing a labeling process. And you can see that these things are changing and you can take action on that.
A block of text above a bar with buttons, a few of which are labeled part-time, full-time, and both.
This is a tool at Indeed called Labeler. It is used to label data. It is not pretty, but it is very effective. And what we're showing here is a chunk of text, which is a job, and then some buttons at the bottom, which are things you can click on. So in Labeler, we ask things like, is this a part-time job? And you can click a keyboard stroke, or you can click it with a mouse, and you can go through this very quickly.
Text. Sometimes you don't need much data.
The first models that our team built for job description classifiers, we sat in a coffee shop for 3 days and labeled 15,000 examples of jobs. And that allows us to build very successful models, even without having very much data. So there are many ways you can evaluate how much data you need to solve a problem. It's related to the complexity of the problem, but it can also be related to how accurate that data is or how clean that data is. But sometimes you don't need very much, because your first model only needs to do better than a simple heuristic. So when we're talking about the job description classifier, maybe our simple heuristic is, let's extract the minimum integer from a job description. And as soon as we can beat that, that's a good enough model to iterate upon.
A line plot titled Learning Curve.
This is an example of a pretty common plot that data scientists use to tell if their models are overfitting. It's called a learning curve. On the x-axis, we have a number of samples that we're using for building a model. And on the y-axis, we have a score. And we have 2 lines here. One is for our training set, and one is for our cross-validation, our holdout set. And what I've noticed here, and what I've seen in this before, is that sometimes you really don't need very much data to get a pretty accurate model. And this is an example here where you can see at the very left that you only needed 750 data points to get a holdout set test score of like 0.83, which for an F1 score or for an accuracy score is actually plenty good enough to deploy a V1. And so I've seen this a lot. I think it's really important to try to build a model on a smaller amount of data. Look at this plot to understand that if you're working on a similar problem, that maybe you don't need as much data as you think you do.
Text. Now train others to label.
So once you've built that V1 and you've iterated on it a little bit, this is your opportunity to take advantage of others to help you label your data. And there are a lot of things you need to remember about others and having them label your data. One thing is that maybe you want to take advantage of an expert to do that. So when we talk about our applicant quality models, so models that take a job and a resume and try to determine how good of a fit they are for each other, our team is not an expert at this. We don't know who the best fit is for this particular role. We're looking at all types of jobs and all types of applicants in the US. So for a healthcare job, a healthcare recruiter may be a better fit, or the actual employer themselves. So we take advantage of experts when we can to label our data.
Check their consistency.
Whenever you involve someone else in your labeling process, though, you need to make sure you understand if they're consistently labeling things. So Mechanical Turk and other examples of this is a really important concept. Sometimes you do majority votes for labeling. Sometimes you look for outliers in labelers and make sure to throw out that data.
Can build next generation model quickly.
But once you've set up this process where you have others helping you label, you can use that over and over again. You can have that run after you've released your first model, and now you have accumulating training sets all the time to build better models or models with more data.
Always flag weird data.
My favorite part about labeling data and looking at data in general is that you always find something weird about it. And weird data can represent a number of different things. One of the things it represents is scam or spam, which is an important problem that you may want to remove. But it can also represent things like changing data. So maybe my data or a feature has appeared more or less over time.
Second step after label data, extract features in one place.
Extracting features in one place.
Diagram begins with feature extraction with lines that extend downward to a bar, which begins with features, then model builder, model predictor, and predictions.
So before, when I showed the IPython notebook and I showed feature extraction between like your training and serving time, I kind of showed a nice example of you just imagining a world in which that code is exactly the same. But realistically, it's not. And one of the ways that you can make it the same is by pulling out your feature extraction, decoupling it from your model building and your prediction. So here we show that feature extraction is separate from when we generate our features and build our models, and it's used again, the same exact code, for when we do our predictions.
Prevents feature inconsistency between train/serve time.
So what this allows you to do is have the same exact code that accesses the same set of data when you do feature extraction, so you don't have to worry about inconsistencies between your training and your serving time. This comes at a cost in that it's really fun and really common to use things like pipelines to tie together feature extraction with model building. But the benefit you get here is that you don't have to worry about different sets of data and changing data over time. It also allows for much faster feature iteration. Since you're not replicating and rewriting feature extraction code between your deployment and your training, you're writing it in one single place. You get to use it as soon as you want. You add a new feature to your feature extraction code, you build a new model, and you already wrote the code to deploy it. The last thing is it really encourages feature extraction reuse. So sharing this feature extraction code with other teams or with your own team or improving it over time. By separating it, we allow that to be a standalone thing.
Text deploy feature extraction services.
So at Indeed, we do this by deploying feature extraction services. So we decouple these features, but we also deploy actual services that will access raw data the same way we would in a deployment environment and do the feature extraction there. So you have a feature extraction service now, and that service is what's going to generate your features, which you can use to build your model with.
Job description of senior software engineer.
So this is an example of that job description we showed a little bit earlier.
Job description with arrow that leads to box labeled Job Description Feature Extractor.
We can pass it to our job description feature extraction service, and we get back results that are very simple. So in this case, we passed in a raw job description to a feature extraction service, and we got back a set of features, which are a string to double map. So things like the experience word in 5 years and counts of 2 to 5 years.
Third step, reuse your model building code.
So another nice side effect about pulling your feature extraction code out of your entire process is that now you can reuse your old model. You can reuse your model building code. Your model building is completely separate from your feature extraction and from your deployment. And so really, when you think about the things you do here, every time you build a model, what do you put in an IPython notebook every time that you do something? You do these things over and over again. You do feature sampling or scaling or selection. You do your test and train splits. You run cross-validation on a grid search or a randomized search. And then you generate plots and you attach those to some tracking software and you show off your model. But these steps are the same for every model you build. Supervised machine learning models go through the same steps. There are just different parameters really to tweak. So indeed, we build a tool, which is our model builder software, which allows us to kind of wrap around scikit-learn to build models that just repeats these steps and allows you to configure them.
11 lines of code which ends with mail _ equals Benjamin1 at Indeed.com.
So this is an actual example of an 11-line file that we use to build a machine learning model that does a number of interesting things. So you can see that there's an input file and an output directory listed. You name your model, you give it a version. And in this case, we pass in a model type, which is a random forest classifier, which is a scikit-learn object. We pass in a set of parameters that we want to run a grid search with. This time we're trying different numbers of estimators and different numbers of max depth. And maybe we want to handle sampling. We know that we have more majority class data than minority class data, and we want to make sure that sample is at kind of 1.75 to 1. We also want to add in some feature selection, so we reduce our feature set. And maybe there's some variance retained information that we need to pass in to get that. And lastly, we want to generate another plot of a learning curve. At the very bottom, we want to send an email of the results. So I can kick off this model build. I can go walk away and play pool down here or grab a beer or something. And then I get a little email when my model's done. And I can go check on the results. So I think this is pretty awesome in that since we removed the feature extraction code away from our model building, now our model building can be completely parameterized. We can work on this as a team. We can have consistent conversations about what happened. I can talk to another data scientist about what steps did you take? How did you do that? And all I have to show them is a configuration file because we worked on the code that implements that together, and we know that it's safe and tested and robust.
Line on a plot titled ROC curve. False positive rate on x-axis and true positive rate on y-axis. Line sharply increases to 1.0 then flatlines.
So here's some examples of things we generate from our model building code, things like ROC curves. We generate nice feature importance tables and obviously actual quantitative results of the model.
Text output your models into a standard format.
So going back to that diagram where we showed model building and model serving separate with the feature extraction kind of in between, it's really important to output your models in a standard format. And this allows you to be able to easily go from one language to another if you want to deploy a model.
Deploy quickly.
So if we have a standardized model and we have a separate feature extraction service, we can now deploy models very easily because all we have to implement is some code that can take our model and make predictions with it.
Diagram begins with feature extraction and model and leads to model predictor, then predictions.
We get to reuse that feature extraction code to actually go get our features from raw data. Maybe in this case, because we're doing predictions, it's just one single example. We need to load in our model into memory and have code around how to do predictions with that code. There's actually plenty of open source libraries that do this. And then we need to make predictions, and this is all we have to deploy.
Text, putting it all together. Diagram with feature extraction at top with lines that extend down to a bar that begins with features, then model builder, model predictor, and predictions.
This is back to that plot earlier that I showed, which shows how everything fits together. So if we're building a brand new model, we write some feature extraction code, maybe as a library to start with. It extracts our features. We can use that as a matrix. We can pass that into our model builder with a configuration file, maybe in our case only 11 lines. That builds us a nice model that we write out into a standard format. And then we have our own model predictor code or third-party implementation, which wherever it needs to be used, on the website or on a mobile app, calls a feature extraction code to extract our features, and then uses our standard model to do a prediction and sends that back to the consumer.
Step 4, release softly and log everything.
So now that you have this nice framework to do a feature extraction and reuse your model building code and be able to deploy things quickly, how do we actually release a model?
Job description on phone, digital graphic designer.
I'm going to go back to an example that I discussed at the beginning of this presentation, which was for the applicant quality team, where we were talking about adding a your resume matches this job text to a job description that you're looking at based on your resume information on your phone. So when we first started testing this, we were a little worried. View job hits happen all the time. Job seekers are looking at jobs constantly, and we didn't really want to release this test just out to the wild at 100%. We were scared about it. So we took advantage of another tool here at Indeed called Proctor, and there are great talks. There's actually a great talk, a tech talk on Proctor that I encourage you to go see.
A bar reads Proctor test for view job evaluation test. Large control section before test 1.
But we did something we call a soft release, which is that we decided we are going to set up a test in which that test would decide whether or not to call our model and possibly display that your resume matches this text. And so we started this test at like 5%, so 5% of all of our mobile users would see this if it was appropriate. And we could look at things like model performance. Model performance in did people click on these things and did good things happen, but also model performance in that how did this affect our actual application? How did this affect the mobile app? Did we slow things down? Are people still clicking on jobs the same?
Control section becomes smaller while test 1 enlarges.
And then we started ramping it up. So we went up to 10 or 15%, and then we eventually get up to 50%, and really up to 100%. So this is how we do something we call a soft release, which is that we can slowly eke things out into the real world and make sure that they meet the criteria we expect them to before we release them to everyone.
Text, log everything.
Logging is an essential part of any organization who does data science or does analysis. And Indeed, we log everything.
Block of code.
So this is an example of an actual log that we generated when we did a view job evaluation for a candidate. And we write out all of our features. And we actually have a decent number of features that we use for these models. And this is kind of overwhelming. But it's an example of we really do log everything. We log predictions, we log features, we log results. And this gives us a number of really awesome benefits. We can reuse these logs when we want to build a model in the future. We already did the feature extraction. Feature extraction is one of the most expensive parts of doing data science live on a website. Now that we've done it for these examples, we can reuse that to build our next model. They also give us an insight into our data. Maybe that data is changing. We can look at individual features and see how they change over time by looking at log data. And we can look at overall predictions and see how those change over time.
Logs allow us to see what went wrong.
Logs are commonly used for other tools to really see what went wrong, and we get to use that for data science too. So we can see that we're not generating the right features. Some of the features are 0. We're not generating any logs. Those things are really valuable to understand that something's going wrong.
Step 5, validate and review every model.
Any good data scientist has transparent and useful work that they validate both qualitatively and quantitatively.
Indeed, model builder. 5 columns each for training set and test set, with labels class, precision, recall, F1 score, and support. Numbered data populates the columns.
Quantitative validation is something that every data scientist does. It's generating things like training and test scores for your precision and your recall and your F1 for classification model. And it's sharing this with other data scientists to encourage transparency, but also to say, I'm ready to release this model. Creating things like ROC curves and plots like that to show that your model fits really well.
Line chart titled ROC curve.
This is an actual ROC curve from the job description classifier model I showed earlier. But at Indeed, we also think about qualitative validation. And again, we have the benefit where we can look at data that is human readable, job descriptions and resumes.
Job description for vice president with highlighted words, like bachelor's, and 5 years.
And so we created a tool that we call Job Description Viewer. And this allows us to thoroughly evaluate the qualitative reasons our models are making decisions.
6 classifiers: experience, education, license, pay, time, supervising.
So zooming in here, we have 6 different job description classifiers that we've deployed. And these are all classifiers, so they're telling different classes apart, not regressors. And we have one that's an experience one that's trying to tell if this is a new 0 to 1 years of experience job, 2 to 4, or 5 plus. There's an education one, which is looking at high school or college. There's a license one. Does this job require a license? We look at pay type. Is it hourly or salary? We look if it's a full-time or part-time job, and we decide if this job requires supervision or not. And so we've created this tool which highlights at the top which classes we think are most prevalent. And we do this by showing actually transparency. So the brightest colors mean that that class is most probable. And so here's some text where we actually highlight the individual words that were used to make a decision. And I always find things like this really illuminating. The first thing that you can notice is that some words don't really make sense on their own. Words like field or knowledge. Sure, that lines up with college, but I don't really see why a classifier is making a decision using that. And it kind of shows that as humans, we make decisions, especially on data, much differently than machines make decisions on data. There's some other examples here. At the very end, we see the word preferred. And by itself, preferred doesn't seem very important. But when you think about how a machine may be using this, it's possible that it thinks that preferred co-occurs with things like degree. Also seen here is that Series 7 and Series 24 aren't highlighted, yet our model still came up with the correct prediction that this is a required license job.
Text, review your models.
So with quantitative and qualitative feedback, we can have a good idea about if a model is good or not. But at Indeed, we take that a step further. And then we do model reviews. This is very similar to a code review. We involve another data scientist in the process to help us decide if this model is ready for production.
Another perspective.
Model reviews provide another perspective, and other data scientists who may have a different set of skills can provide advice and feedback. Model reviews also encourage transparency and reproducibility. You need to share the steps that you took to solve your problem, all of the different facts from accessing data all the way to deploying your model need to be kind of illuminated for someone to understand what you did. And reproducibility, we always encourage and expect data scientists to include all of the artifacts necessary to regenerate a model. The last part about a model review is that it gives you awareness of other data science work at the company. So at Indeed, we have data scientists in all of our offices in Tokyo, in Seattle, in San Francisco, and here in Austin. And we do model reviews across offices, which allows us to really see the kind of work that's being done, the great work that's being done in different offices.
1. Context. 2. Data. 3. Response variable. 4. Features. 5. Model selection and performance. 6. Transparency and recommendations.
There are 6 main categories that we include in a model review. We look at context. How are we going to use this? We look at information about the data. What are we trying to predict? What kind of features did we use and how did we use them? How did we choose the best model? What was the performance of that model? And lastly, what's some information about this? How are we going to use this? What's the recommendation for when we should release this model? Model context. What is this model going to enable us to do that we couldn't do before?
text, highlighting, filtering, sorting, etc.
How are we going to initially use this model, and how will we possibly use it in the future? For our data, where did we get this data from? What queries and filters were used? Did we sample our data set? What time range did this come from?
Response variable. How was the response variable labeled or collected?
What are we trying to predict? How did we get that data? Is it data from an employer or from a job seeker, or is that data that we labeled ourselves? And how did we label that data? We share the labeling task if we use it, and we describe the assumptions that we made when we do labeling ourselves. And how should we use the predictions? Are they predictions that are meant to be used to understand if this is a good recommendation? Are they probabilities? Are they counts? How do we generate our features? Which features were the most important in our models? And really the heart of a model review is the performance of that model. What was the train and test set performance? How did we do cross-validation to choose our best model? What kind of scoring function did we use? Did we have a new holdout set that we get for free because we trained others to label our data? And lastly, what's the expected model performance? And not necessarily just from like an F1 standpoint or an actual metric, but also from what's the impact going to be to our website using this model. In the last bit of a model review, we include things that are related to transparency. So we include all the properties files we use for our model building. We include links to code that we may have used for generating our features. We show examples of our model predictions. We show examples of qualitative and quantitative feedback. And at the end, we write a nice summary, which is, this is how I think we could improve this model in the future, and this is why I think it's ready. So that's a lot. You're asking a data scientist to write up the entirety of this thing, and what's the value there? The value is kind of twofold. One is that the person who's going to come in and build the second version of this model, they need to know all of these things. And likely that person's going to be you. So you're reminding yourself, these are the things that I did. When you go back and look to build that V2, you can know, oh, I did try that feature and it didn't work because you documented it well. You can pull up that code that you use to generate your features and reuse it. You can use that property file to run the next version of your model and think about different parameters. You can look at your possible directions and future improvements as guidance to yourself 6 months later when you're building the second version of this model. And the second benefit is that others who want to know what you did and understand it and challenge it possibly can go look at this extensive documentation and really understand what you did and what steps you took.
Step 7. Monitor after deploying.
So after you've done a model review and you validated your model and you're ready to put it into production and you deploy it, you have to start thinking about, what do I do after I deploy this model? So one key fact is that in software engineering, libraries are dependencies, and if you change a library kind of underneath you, your code doesn't compile. But in data science, your hard dependencies, if they change underneath you, your model still makes predictions. And so you really have to think about that and understand that features and data are hard dependencies for data science. We have to understand how features and data are changing while we're making predictions. We also need a post-deploy plan. What happens if something goes wrong? What happens if my model starts making crazy predictions? What happens if I say every applicant's a good fit for the job? What do I do?
Use log data to check for feature changes.
So another benefit of logging your data and logging your features is that you can use this to actually automatically check for data changes over time.
3 bell curves on a plot with TF-IDF Excel on the x-axis and bucket count on the y-axis.
This is another pretty simple tool that we use in Adeek called Log Viewer, called Feature Monitor. And it does a pretty simple, it has a pretty simple task in that when we build a model, we can look at every distribution of every feature, and we can do a plot of that. So in this plot here, we're showing one single feature, which is a term frequency inverse document frequency value for the word Excel. And we can make a plot of what that looked like when we trained our model. And then every day that we're making predictions, we can also make a plot of what that feature looks like on the day we're making a prediction. So in this case, the model was trained with this blue kind of histogram here shown, and the model was evaluated yesterday on this yellow histogram. And what we can see pretty easily and visually is that there's a difference between these two histograms, that it kind of shifted to the right. And so that's a problem. We're worried that this could be a bad thing. We run a bunch of different statistical tests to really confirm that, and at the top we show some examples of that and their p-values. And we send an email out to everyone on our team that says, hey, this feature looks weird, you should investigate it, and we do. One of the easiest ways to check to see if your model is doing something wrong, however, is to look at class distributions or predictive values. So if your model is a regression model, you can just look at kind of what does the histogram look like for the regression values I'm predicting day to day. And if that's shifting in different directions outside of the normal, you know something's wrong. Within classification models, you can look at the ratio of different class predictions. And if that changes over time, you know something could be wrong.
Step 8. Retrain when needed.
Many data scientist teams set up model retraining to happen daily. And one of the reasons why that may not be a great idea is that if we agree that every model should be validated both quantitatively and qualitatively, retraining a model is not just expensive to retrain it, but it's also expensive in the time of others who are doing model reviews or looking at this information. I will add a caveat here that there are models that you don't really have an option here and that you need to take advantage of fresh data and retrain consistently, but many models don't need to be. And in that case, I discourage just automatically setting up a daily train. I encourage that you retrain as necessary. So one of the things you can do is you can use the feature monitor tool or a feature monitor tool of your own to determine if your features are stable over time. And if your features are stable over time, you likely do not have to retrain your model as often. You can also just choose to use less sensitive features. So some features are very unstable and there are alternatives to them or normalization factors you can use on them to make them more stable. If you have a growing website like we do, we try to avoid counts whenever we can, for example. We try to find normalized values. Counts always increase over time. 3 months from now, I'm guaranteed that that feature distribution is going to look different than the one does today.
Text, full stack data scientists.
I've discussed a bunch of different topics and kind of pointed out some key things that I think are important to full stack data scientists. And indeed, we expect a single person to be able to perform each of these tasks, from gathering data to deploying models and really monitoring things. And that involves a lot of different knowledge, from statistical knowledge to machine learning to software engineering to communication. But really what this talk was about, especially the second half, was full stack data science organizations. And I wanted to talk about each of the individual steps that you need to think about and how you should solve that problem.
More Indeed Engineering. Engineering blog and talks, Indeed.tech. Open source, opensource.indeedeng.io. Careers, Indeed.jobs. Twitter, @IndeedEng.
Thank you for your time. You guys can check out other engineering blog and talks at Indeed.tech, especially the Proctor one, which is for A/B testing. Go look at our open source software that we release, including Proctor itself. Tweet us at IndeedEng. Thank you.
@IndeedEng. Tech Talks at Indeed's Austin headquarters. Engineering.indeed.com.